welcome you all to the today's session of UK Ghori Alumni Series. Now, I would like to request Zishan to please come forward for the recitation of Holy Quran.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم هو الله الذي لا إله إلا هو عالم الغيب والشهادة هو الرحمن الرحيم هو الله الذي لا إله إلا هو الملك القدوس السلام المؤمن المهيمن العزيز الجبار المتكبر سبحان الله عما يشركون هو والله الخالق البارئ المصور له الأسماء الحسنى يسبح له ما في السماوات والأرض وهو العزيز الحكيم صدق الله العظيم.
Jazakallah khair for the beautiful recitation. The QK Ghori Alumni Seminar Series, organized by the Department of Mathematics, is a platform where distinguished alumni returns to our university to share their expertise and inspires current students. It is named in honor of esteemed mathematician Dr. Karamuddin Khan Ghori. Today, about the guest, Dr. Waleed Noor completed his BS in Mathematics from COMSATS University Islamabad in 2007, being among the very first batches of the BS Mathematics program. He then pursued his PhD at the Abdus Salam School for the Mathematical Sciences, Lahore, and later went on to undertake postdoctoral research across Europe, including University of Barcelona and Oslo. Currently, he served as a tenured associate professor at the University of Campinas, Brazil, which is ranked among Latin America's top universities. His research connects operators theory, complex analysis, and Hilbert spaces for the holomorphic function, addressing deep problems in analytic number theory. His remarkable achievements include receiving the inaugural Abdus Salam Medal from the Pakistan Mathematical Society in recognition of his outstanding contribution. Without further delay, I would now like to invite Dr. Sahibzada Waleed Noor to deliver his talk on the topic A Hardy-Hilbert Space Approach to the Riemann Hypothesis. Over to you.
Sorry, I think my mic was muted. Thank you very much. Can everyone hear me clearly? Is my voice?
Yes.
Yes, sir. Yes, sir.
Okay. So I'll obviously give the presentation in English, लेकिन उर्दू भी बीच में बोल सकते हैं. I'll just so thank you so much for inviting me, and it's quite an honor actually to be back giving a presentation. I wish I could be here in person because obviously I have so many fond memories as an undergraduate student in COMSATS Islamabad. This was 2003, in fact. I think it was the first or one of the first batches in bachelor's. And I remember our teacher for calculus, the very first course was Professor QK Ghori. So it was quite an honor. And of course, Professor Ghori's books were the standard calculus books, I believe, that were studied in in BSc. Although I believe in BS mathematics, we used a different calculus book. But no, I have very fond memories of my time in COMSATS, and I hope all of you also have a wonderful experience. So I think I'll start by sharing my screen. I don't use Teams that often, so I have to figure it out. If someone can help me. How do I share my screen? Is it this desk view? No, this is not it. Share. Okay, I found it. Share screen. Um, can everyone see my slides, my PDF?
Yes, sir. Yes.
Okay, excellent. So my goal in this, so I had to think a little bit how to present um, some of these ideas. So I decided in the end to give a more broader perspective and then eventually lead to more recent work with my students and collaborators on the Riemann hypothesis. I'm sure many of you have heard of the Riemann hypothesis as one of the major open problems in mathematics for more than 100 years. Uh, but my approach will be to first try to introduce some of the objects from my own area of research, which are not historically related to the Riemann hypothesis or number theory, to try to uh, introduce those objects first. So the topic won't be easy, of course, but I will try to motivate it as best as possible. Because as Professor Sohail Saab, and of course I forgot to mention Sohail Saab, of course, Professor Sohail Saab, he was our teacher, our tutor, TA in our abstract algebra course, and I do remember having very nice discussions with him back then. This was before he went for a PhD. So I would like to thank him, of course, for extending the invitation. So I'll just start with the talk. So uh, the first slide will be about Hardy spaces over polydisks. So these are the real main objects of our study. Now, what are Hardy spaces? Basically, these are spaces of holomorphic functions. So maybe some of you have studied complex variables course in bachelor's, because I remember we had a complex variables course in the fourth semester, I think, or fifth, where we used Churchill's book. So uh, Hardy spaces are spaces of analytic functions which are defined on copies of disks. So by a disk, open unit disk, of course, I assume you know what that means. These are complex numbers with modulus less than 1. But these spaces can be defined on one copy of a disk or two or three up to infinite copies of the disk. So the definition seems a little bit technical, but it is not as technical as it seems. So the Hardy space H2Dn is a Hilbert space. So I assume you know what a Hilbert space is. It's a space with an inner product of functions which has norm defined by this. So a norm, of course, is like absolute value that we have in Cartesian spaces. So it is defined like this. So it's the supremum of the integral over Tn. So Tn is what we call the n-dimensional torus. So if you imagine a copy of a disk, so the frontier, the boundary of the disk is a circle, a unit circle. So now if you have n copies of the disk, then the boundary or the distinguished boundary is n copies of the circle. So this isn't a single integral, this is a multiple integral, an n-dimensional integral over n copies of the unit circle. So this is the definition of the Hardy space. So these are basically analytic functions, holomorphic functions, but the difference is that they're not holomorphic functions only in one variable. Depending on the value of n, they can be in many variables. They can even be in infinitely many variables. So we'll talk about these things and how they're related. So one of the distinguishing features, the key distinguishing features of these Hardy spaces is that they are what we call reproducing kernel Hilbert spaces. So you have many Hilbert spaces. Maybe some of you have heard of the sequence spaces or L2, the measurable function spaces. Actually, maybe I should ask, what is the general audience? We have undergraduates, right? It's BS mathematics. Yes, these are undergraduates. So uh, so what is special about these reproducing kernels is that these spaces have elements which have the special property that when you take the inner product with a particular function, so in this case, this is the reproducing kernel at a point in the n polydisk. That means these are copies of the unit disk. So when you take the inner product, it gives you evaluation. So what makes this really special is that these are spaces where the Hilbert space or algebraic operation can be used to determine evaluation, which is a function theoretic operation. So in other words, you can do operations which are related to functions by algebraic operations, which such as an inner product. Okay. And what is unique about this is that in the infinite dimensional case, when n is infinite, this reproducing kernel resembles the Riemann zeta function. So this is really the definition of a Riemann zeta function. So it's a series of this form. So it's an infinite series in the variable s, where k is an integer. So this is really the Riemann zeta function, the classical Riemann zeta function. And Euler, of course, proved his famous product formula because, a natural question is, why is the Riemann zeta function related to primes? And it's because of this product formula. Okay, so this is a product over all the primes. So one can see that actually there's a curious connection between this Euler product formula of the zeta function and the definition of the reproducing kernel in infinite dimension. So it's kind of a hint that there's maybe some relation with the zeta function. So another major open problem that has always been important for these spaces is the question of invariant subspaces. So what is an invariant subspace? So this Hardy space, these are infinite dimensional vector spaces. From linear algebra, you've studied linear spaces. So these are linear spaces, vector spaces, but they don't have finite dimension, they have infinite dimension. So one of the major open problems is to understand invariant subspace. So what is an invariant subspace? It is a proper subspace E inside the space such that if you multiply by the independent variable zk, because remember, these Hardy spaces are function spaces which contain polynomials. So if you multiply by a polynomial and it sends the subspace back into the same subspace, it leaves it invariant. Okay, so then we call it an invariant subspace. So in fact, the problem of characterizing these invariant subspaces is actually, for all dimensions greater than 1, is actually still a major open problem. So another major open problem is called the invariant subspace problem for the shift. In fact, to see basic example, it's not difficult to construct invariant subspaces. So for example, if you consider the subspace of all analytic functions, holomorphic functions in this space, which vanish on some subset S. So you choose a subset in the disk, in the polydisk, fix any subset, and you say, give me all the functions which are 0 on this set. So this actually is a vector space. And this is in fact an invariant subspace. Okay, because by multiplying by the independent variable, you again get a function which vanishes on the same set. Okay. By the way, if anyone has a question, you can, of course, ask me. So this question of invariant subspace, historically, was proved in the case n is equal to 1. It was already a major open problem, and it was actually solved by Arne Burling in 1949. So this is, I'm trying to give some history of this as well, because this was really the starting point of Hilbert function spaces. The whole theory of Hilbert function spaces really started with this result, because this result was originally considered by Hilbert in a different context, actually. And it was Burling who translated this open problem into the Hardy spaces and gave a very beautiful solution. So the solution is that a
Uh,
subspace E is G. Yeah,
is
yes.
it kind of equivalent to the classification of the rank 2 vector bundles?
Uh, I couldn't really say, but because the language of vector bundles, my friends in algebraic geometry are better at, but it is related to, yes, it is related, it might be related to, it is related to the question of characterizing submodules in certain Hilbert modules. So, but I can't really say because I not haven't been studying the language of vector bundles. But I wouldn't be surprised if it is. In fact, this question in higher dimension, Dr. Sohail Saab, is in fact more recently there has been techniques from algebraic geometry and complex geometry that have been used to try to solve it in higher dimensions. But in one-dimensional case, it's purely a function theory problem. But it was solved. So when this was solved, people were surprised because it was originally an algebraic problem. But until now, the only solution we have is using Hardy spaces or analytic functions. And the solution was that E is an invariant subspace if it is equal to a function phi, which we call an inner function, multiplied by the whole space. So what this means is, what is an inner function? So they defined an inner function as a function. So remember, these functions are defined on the unit disk, but they're not defined on the boundary. They're only defined almost everywhere on the boundary. Almost everywhere is terminology from measure theory. That means they're not defined at all points, but they're defined almost everywhere, and that they should have modulus equal to 1 on the boundary. So this was a huge breakthrough. It started this whole area of mathematics called Hardy space or Hilbert function spaces. So in fact, until now, we don't have a different solution to this problem. But for n greater than 1, this remains an open problem. When you have more than one variable, in fact, Dr. Sohail Saab, you probably already noticed here that just looking at this, that these are varieties, right? These are zero varieties. So there seems to be a correspondence between the zero sets and invariant subspace. And this connection is a part of multivariable operator theory and its connection with algebraic geometry, actually. So there is a connection there, and work of Douglas, etc. In fact, Hilbert models has exploited this connection, in fact. And that's actually why it makes it difficult. So even in algebraic geometry, of course, this is for Sohail Saab, because maybe students aren't aware, already in one complex variable, the zero sets are discrete points. So they're not very interesting from a geometric perspective. But the moment you go to a higher dimension, two variables, any analytic function or polynomial in two variables, the zeros are never isolated. The zero varieties are much more complicated. So this is in fact believed to be one of the reasons why this question is also so complicated, because of this complexity of the zero varieties. But there's more invariant subspaces than zero varieties. But what's more intriguing is recently it was discovered that the same problem in infinite dimensions, meaning that you have holomorphic functions with infinitely many variables, and the domain is infinitely many copies of the disk, seems to be very intimately connected with the Riemann hypothesis and another problem called the periodic dilation completeness problem from harmonic analysis, which, okay, we don't need to talk about that, but they found some indirect connection with the Riemann hypothesis. So I have a lot of slides here. Maybe I don't need to talk about all of them, but I do want to talk about perhaps the invariant subspace problem. So in general, so there's a more general problem. The major open problem in operator theory is called the invariant subspace problem. So what it asks is that given any complex separable Hilbert space, meaning an infinite dimensional separable Hilbert space, and you have any bounded linear operator, does this operator necessarily have a non-trivial invariant subspace? So this actually has been open for almost 100 years now. And it was asked by John von Neumann when he was formulating the mathematical theory for the basis for quantum mechanics. So he was interested in invariant subspaces from that perspective. And it is usually believed that John von Neumann was the one who formulated this question, and it is still an open problem. But what's interesting is that in finite dimensions, this is always true. And in fact, the students here will know why it's true, because a linear operator in finite dimensions is just a matrix. And from linear algebra, it's a square matrix. And from linear algebra, you know that square matrices always have eigenvectors. They always have eigenvectors, and you're taught techniques to find those eigenvectors. You do the Gauss elimination, you have the characteristic polynomial, and then you find the determinant, and there's ways to, so it always exists an eigenvector. An eigenvector is a one-dimensional invariant subspace. So in finite dimensions, this problem is always true. There's always a non-trivial invariant subspace. But what's more interesting is that if you go to very high dimensions, like non-separable means so it's very large. It's a very large, the dimensions. We can't give it a number, but it's much larger than the smallest infinite dimensional space. Then it is also trivially true. But so it's only in the separable case that this remains a major open problem, and this is the most important case, of course. So this slide is basically about, so universal operators were discovered in 1969 in a paper by Carradus, actually in 1960 by Rota. So Rota is a very famous mathematician, in fact. So he discovered these very interesting operators, this interesting phenomena that only occurs in infinite dimensions. So that's one of the themes, because my research has always been in functional analysis, which is basically linear algebra, but in infinite dimensions. So what we always see is that because of infinite dimensions, very curious phenomena occurs, unexpected phenomena occurs. So for example, this discovery of universal operators, so what is the definition? It is one operator which contains within it properties of all operators in a very particular property. So for instance, the exact definition is that, of course, U is universal if any other operator T that you choose, you can find some subspace for this universal operator such that the restriction of this universal operator is similar to T or similar to a multiple of T. In other words, by restricting this one universal operator to its subspaces, you can study every operator, any other operator that exists. And remember, the space of all operators is very large. So if you have infinite dimensional space, then the space of linear operators is much larger than, for example, the space of continuous functions or the space of the usual functions you study in calculus, differentiable functions. This is much smaller infinity compared to the space of bounded linear operators, which is very vast. Okay, so this is another very curious phenomena that surprises people, that why does such an operator exist, that just studying its restrictions, you can study some properties of every possible operator. And in fact, Carradus in 69 gave a very nice criterion as well, that you can discover this universal operator by the following very simple sufficient condition from linear algebra kind of condition, that if the kernel is infinite dimensional and if it is surjective. So that's enough. If it's infinite dimensional and it is surjective, then U is universal. So this is a very easy criterion to satisfy. So I think I will ignore this slide for now, and I think we'll go straight to the main topic. Actually, the previous slide that I missed, I was about certain results related to universal. With my students, we were able to discover certain examples or characterize certain universal operators, but I think for the moment, it is not so necessary. So I think we should come to the main topic. So that was just the introduction. So my goal with the introduction was to show how the Hardy spaces are infinite dimensional spaces, but in these spaces, you don't have individual points, but you have functions. The points are functions in one variable, two variable, or until infinite dimensions. But of course, these are different spaces. So the one-dimensional space, the space with one variable functions is different to the space with two variable functions, is very different from the space with infinite variables. These are all different spaces. They are isomorphic. So maybe you guys have studied linear algebra and abstract algebra, you know the notion of an isomorphism. So we say two structures or two spaces or two objects are isomorphic, or in the case of topology, homeomorphic, if all the underlying structure is similar, is identical up to an isomorphism. So from the point of view of abstract algebra, we say two groups are isomorphic if from the perspective of the algebraic operations, they are indistinguishable. They are the same, basically, right? So all separable Hilbert spaces are isomorphic. So in other words, you can have one copy of a Hilbert space and another copy of a Hilbert space. From a Hilbert space perspective, they are all identical, but that doesn't mean that they are the same in terms of their utility. So the Hardy spaces are just one copy of an infinite dimensional Hilbert space. Okay, you can have any other copies, but it's the most prominent and important copy because it's the most widely studied. Okay, and also because it has analytic functions inside it, and it's a reproducing kernel space. Okay, so let's start with the Riemann hypothesis. So first, the Riemann hypothesis postulates that all the non-trivial zeros of this function. So here, of course, I've cheated a little bit because this function, this series actually converges only to the right of the real part is equal to 1, this half plane. It only converges here, and it's not difficult to show. So, but Riemann himself proved that it is possible to give an analytic continuation of this function to the rest of the complex plane. Okay, but of course, once you have an analytic extension of this function, it is no longer defined by the series. Okay, in fact, it then becomes a function with trivial zeros. These are called the trivial zeros. -1, -2, -4, -6. The negative integers, even integers, are called the trivial zeros. And the point 1 is the unique singularity. In fact, from calculus, you know that if you put s is equal to 1 here, you get your, which series? It's called the P series, or I believe in calculus we call it the P series, or is it called the geometric series? No, it's not the geometric series, P series, I think. So if the series 1 over n diverges, right? And that's exactly why the point 1 is a singularity. So the Riemann hypothesis states that all the zeros lie on this critical line. So when the real part is 1 over 2. In fact, Hardy himself, G.H. Hardy, the very famous, maybe you've seen the movie. G.H. Hardy was the person who, the great British English mathematician. This is pre-partition. He invited Ramanujan to England. You've heard of the story of Ramanujan, perhaps, the famous Indian mathematician. So this is the same Hardy. In fact, he was the one who proved that there are infinitely many zeros on this line. But to date, no one has been able to find more zeros. But it is known that if there is a zero outside the critical line, then they are symmetric. So if there's one here, then there will be one here also. Okay, and there will be one here, there'll be one here. So the question is whether they exist non-trivials. Until now, using all the computational power that we have, no zeros have really been found uh, outside the critical line. Now, of course, we need more time to explain why this is related to why this is such an important open problem, because it's related to the distribution of primes. Um, uh, so the existence of zeros or non-existence of zeros is intimately related to the question of distribution of primes. Maybe we'll talk about it ahead. So now I want to discuss the starting point of my research in this. So my goal really was, since I was studying Hardy spaces, which have no connection with number theory per se. So I always wanted to try to find a way to maybe bring the Riemann hypothesis or questions around the zeta function to the Hardy spaces and try to use all these tools. And I was very fortunate because then I realized that there's a Bjorling actually had a result related to the Riemann hypothesis. So the same Bjorling that solved the subspace problem for the Hardy spaces. So him with his PhD student Nyman, he had made this beautiful criterion. It's called the Nyman-Bjorling criterion for the Riemann hypothesis. It is the most well-known and perhaps the only one I know, which is a reformulation of the Riemann hypothesis as a question in functional analysis. So he defines these functions. So this is the fractional part from calculus of lambda over x minus lambda into 1 over x, where lambda is any real number between 0 and 1. Now, looking at these functions, this isn't a very complicated function to define, of course, but trying to make a graph of it is probably not very easy. So because of this, what I've done is, in fact, I have plotted it for you guys so you can have some idea. So what I've done here is I've, instead of lambda generic, I've put lambda is equal to 1 over 2. I've done this because if I put lambda is equal to 1, you can see this function will become 0. So I've put lambda is equal to 1 over 2. So let's see what the graph looks like, just to see if we can find some pattern. So obviously these function, so these functions are defined between 0 and 1. So this is where we are interested. So if you look at the graph, I hope you can see these blue dots. Can everyone see these blue dots? Is it visible?
Yes, sir.
Yes, sir. It is visible.
Okay, perfect. No, I just wanted to know because I suddenly got scared that maybe वहाँ पे कहीं load shedding तो start नहीं हो गई. Maybe everyone's aware. So, so what's interesting about these functions is my computer is probably going to give up, but so these are what we call step functions from calculus, right? In the sense that they look like steps. So, okay, let's start from here, from 1. So let me try to zoom out. So between 0.5 and 1, its value is 0.5, and then it drops suddenly to 0, and then it's 0.5 again. So you see this zigzag pattern going up and down, up and down, up and down. Okay, this is just one function, so it has a very funny graph, right? Now let's do something more interesting. Let's actually, instead of 1 over 2, let's choose, I don't know, let's choose 1 over 5. Sorry, ignore the thing on the right. Let's choose 1 over 5. Now let's see what happens to the same. So instead of lambda 1 over 2, I've chose 1 over 5. So let's see what happens at 1 over 5. Now 1 over 5, see, the graph becomes even more interesting. So instead of 2 steps, I have 5. So 1, 2, 3, 4, right? Yeah, if you start from here, and then it drops back down to 0. And then it's 1 over 5, 2 over 5, 3 over 5, 4 over 5. So it's kind of 1, 2, 3, 4, 5. And then it drops down again. It's almost like a stair pattern. It goes down, then it goes up, then it goes down. But in each step, the closer you get to 0, it becomes smaller and smaller. It becomes so small. You can keep going, but it might destroy my laptop. Hopefully it won't. Okay. So you get the idea. So I'm afraid of putting in a larger value of rather than 1 over 5, but 1 over 100. I'm afraid to do it, but I'm also tempted to do it. Should I do it? Hope I don't break my computer. Then COMSATS will pay for my new laptop. Just joking. So let's put 1 over 100. I think this will, I hope it doesn't crash my, I think it's not even trying to compute. Oh, okay, no, okay. It didn't crash my laptop. Okay. Okay, that's very pretty. I didn't try to do it before. Okay. Interesting. So I assume from the analogy that we saw, we will have 100 steps now. 3, 4, 5, 6, 7, 8, 9, 100. And then it should come back down and start another 100 steps up and then back down. So I assume that is what is going on here. So yes, I think that is what is going on. So you can see these functions are easy to define, but they have very strange behavior, right? So I hope that gave you some intuition of what these functions graphs look like. Now, we're considering all such functions where lambda, we can choose 1 over 2, 1 over 3, 1 over 100, 1 over whatever. So the Neyman-Burling criterion states is that the Riemann hypothesis holds if and only if the characteristic function, so okay, what is a characteristic function? Ignore it. It's just the constant 1. Characteristic function is the constant 1. In other words, if it belongs to the closed span of these functions. in this L2 topology. We don't need to talk about L2. Basically, what it's saying is, I think we should go back to a prettier, let's go back to 5. Oops. What it's saying is that if you can show that the constant 1 on this constant function 1 can be approximated by linear combinations of these kinds of functions, okay, by linear combinations can be approximated, then you have proved the Riemann hypothesis, the major open problem in mathematics. So when I saw this criterion, I was like, wow, this is so beautiful, so elegant, so easy to understand, and there's no reference to number theory or primes. So I like this. Of course, now you understand. So rather than thinking of the Riemann hypothesis as this version, you can just view it as an approximation problem. Can you approximate 1, the constant function 1, with linear combinations of step functions of this form? These very strange step functions, right? Although you can clearly see the pattern, like if it's 1 over 5, then you have steps on 1 over 5, 2 over 5, 3 over 5, 4 over 5, and then back down. 1 over 5, 2 over 5, 3 over 5, back down. Okay? So that was the Neumann-Burling criterion. So some comments about it. So more recently, in 2000 actually, Louis Baez Duarte, in 2003, in fact, 50 years later, he refined this criterion of Baez Duarte by saying that, actually, you don't need to consider all elements in 0, 1. You can just choose lambda is equal to 1 over k, which is exactly what I did. So I chose 1 over 5, I chose 1 over 2, right? You can choose just these, and still you will have this criterion. So Riemann hypothesis if and only if the constant 1 can be approximated by linear combinations of these step functions. So that is the Baez-Duarte criterion actually. And in this formulation, as we saw, each of these functions is constant on these intervals, on each one of the intervals 1 over n plus 1, 1 over n. That's exactly what we're witnessing here. So each such interval where this is constant is some 1 over n plus 1, 1 over n. Okay? And of course, these intervals become smaller and smaller and smaller as n goes to infinity. It gets close to 0 and it becomes smaller. Okay? So yes. So this was the Baez-Duarte Neumann-Burling theory of the Riemann hypothesis, which was my starting point. So then in 2019, well, before 2019, it was 2000, maybe 16 or 17 when I started working on it. I tried very hard to try somehow to transport this very beautiful reformulation of the Riemann hypothesis into the Hardy space of one dimension, because that's where I felt comfortable. And finally, I succeeded. I was fortunate. I succeeded. I can't explain how I did it here, but maybe next time. So this is what I came up with, that instead of those functions with these very funny graphs, we have this kind of simple looking, elementary looking function in complex analysis, which is 1 over 1 minus z times the logarithm, the complex logarithm of this polynomial. Okay, so then if you take the span of these functions, then the Neumann-Burling criterion becomes that the Riemann hypothesis holds if and only if the constant 1, so again we have the constant 1, but now it's the constant 1 as an analytic function, if it belongs to the closure of the span. So again, if the constant 1 can be approximated by linear combinations of these very elementary looking functions. And then part 1 of the main results there was that unconditionally, meaning without assuming the Riemann hypothesis, so if I multiply each one of these functions by 1 over z, so notice what will happen. This factor will be cancelled. So you'll only have log. I was able to prove that actually then it is dense. So this actually supports the conclusion of the Riemann hypothesis, because it turns out that multiplying by 1 minus z is a linear operator with dense range. So in other words, if the Riemann hypothesis were true, then n would be dense. And since 1 minus z multiplier gives you dense range, so this whole thing would be dense under the Riemann hypothesis. But we were able to prove it independently of the Riemann hypothesis. So this is kind of a supporting statement. And as a consequence of this, then if you divide by 1 minus z, this actually shows that N is dense in H2, but in a weaker topology. Okay, so the Riemann hypothesis holds if and only if 1 can be approximated, but we also showed this is equivalent to saying that N can approximate every function in the space. So this is another very interesting criterion. So just by showing that the constant 1 is there, it is equivalent to saying that it can approximate every function if it can approximate 1. This is a very special property. So if you can show density in this topology, you have the Riemann hypothesis. We were able to prove a density in a weaker topology, in the compact open or the topology of uniform convergence, okay, or pointwise convergence, for example. So we can ignore some of these observations here, maybe because maybe Mobius function, So I just wanted to show you what the prime number theorem is. So if you just look here at the bottom, this is before the Riemann hypothesis, before the 19th century, actually since the 18th century, this was the major open problem in mathematics, in number theory, in mathematics. People like Gauss, Legendre, and so many others, even since Euler's time, I believe, or maybe not, but for sure, Legendre and Gauss, they all thought about this question. So at that time, they didn't have calculators. They had these tables of primes. And looking at the primes, obviously, Gauss was such a genius, he actually predicted, I believe, he hypothesized that I can see a pattern. What is the pattern? That the number of primes less than any quantity x, if you look at, like, for example, 100, how many primes are there less than 100, right? This is a function of x. He said that this seems to be growing asymptotically, meaning it seems to behave like the function x over log x. And he predicted this just from looking at the tables of primes. And this was remarkable. And this remained an open problem for several, I think, more than a century at that time. So it was really Riemann's ideas. And in fact, it was one of the main motivations for the creation of complex analysis, one of the main by Riemann himself. That's why you have the Riemann zeta function. He gave the ideas. He didn't solve the problem. He gave the ideas which were then solved in the end of the 19th century. It was actually proved that this is true analytically. So I would give you students an exercise, like just play around with this formula. It's a remarkable formula because it means that if you give like x is equal to 1 billion, you get a very accurate approximation of the number of primes between 1 and billion, which is quite remarkable if you think about it, because obviously it has to be an integer. So you get and also we know from number theory that the primes become more sparse. That means they become more further apart the higher you go. So in other words, the larger number you put in here, you get a very accurate or maybe an exact estimate for the number of primes. Just to give you an idea of how remarkable this is, because remember, primes are distributed very randomly. We still don't understand the primes. Like, why are they distributed so randomly, okay? So the proof of this used the Riemann zeta function. That is, and in particular, the zeros of the Riemann zeta function, or knowing in particular, I can even tell you, knowing in particular whether the zeta function has any zero on this line is equivalent to the prime number theorem in a particular sense. So that is the crucial ingredient in the proof, proving that the zeta function has no zeros on this line. So that is why Riemann was so curious about this. Where are the other zeros? In fact, if you can prove that there's no other zeros except for zeros on the critical line, then you have the best possible convergence or the fastest conversion error estimates for the prime number theorem. That is really the motivation. So obviously, when x tends to infinity, so there's an error for finite x. So you get the best possible error term if the Riemann hypothesis is true. That is the real motivation for the Riemann hypothesis. I think I'll skip this part. I don't think it's necessary. I'm just explaining here some of the work we did using operator theory to understand these spaces, the Hardy space and this new formulation that we had. This is just to give you an idea of the the many different spaces that are required, that need to be traversed in order to bring this Bayes-Duarte reformulation of the Riemann hypothesis to the Hardy space. So this is actually one of the reasons why this area is a little bit difficult, because there's so many different versions, and moving from one to another can be complicated. So I'll try to explain this final part. So more recently, in 2024, with with one of my former students, who's a professor now, Santos, and collaborators from Oxford. Actually, Aditya Ghosh is now in United States, a very brilliant undergraduate student. In fact, he was an undergraduate student when he contacted me. So for many of you students, just to say that don't be shy to write. Even when I was a student in BS Mathematics, where you guys are, I remember I would write to people. I wrote emails to Terence Tao, one of the famous mathematicians, to Stephen Krantz. Walter Rudin, unfortunately, had passed away, so I couldn't write to him. And you will be surprised. I got replies from all of them. So never be shy to, of course, you can write to me also, but write to more famous mathematicians, and they will reply to you with very encouraging messages. You will be surprised, okay? So I'm saying this because Aditya Ghosh actually messaged me, and he was an undergraduate in Oxford. And he had this little project that then we worked on, and which led to a paper actually over the span of 2 years. Of course, we worked on it online. So in order to explain this, I first want to talk about what we know so far about the zero-free region. So you see, I explained earlier that the Riemann hypothesis is the question that all the non-trivial zeros are on this line. But in fact, something simpler, well, simpler, it's not simpler. Another question is still open as well. That is, can we find any half plane, any line here, so that there's no zeros to the right? Can we find any? We don't know. We don't know anything. In fact, if I'm allowed to mark this, let me try my drawing skills. So the best that we have is regions that look something like this. So they get very close as you go higher, and then they taper off, and then they go very close. So I guess, okay, this is not a good drawing. Let me try again. What I'm trying to say is that, yeah, the best kinds of regions that we have, that we know are zero free, look something, okay, it's not that big, it's much closer. The point is that the higher you go, the zero free regions, meaning the places where we know the zeta function has no zeros, gets closer and closer to the point 1. So in other words, we don't even have a proper half plane which is zero free. Even that would be a major breakthrough. Okay, so that is what that table was actually showing. Oops, sorry. That is what is going on. Yeah, so that is what this table was showing, some of the classical results. So if S is the real part plus imaginary part, beta plus IT, so this gives you some of the oldest results. In fact, he was one of the persons who proved the prime number theorem, so some of the best estimates. So what does this mean? So 1 minus beta means how close the real part is from 1. That means how close it is to the line real part is equal to 1. So if you notice, as t gets higher, if you increase the imaginary part vertically, this gets smaller, the distance. So as you noticed, I made that diagram, right? It's like a little bump. So the higher you go, the less we know, okay? Even until now, the latest 2015, we have something like this. So you can see it's very incremental improvements, okay? So no zero-free half plane of this form. CS means real part greater than S, between 1 or 2 and 1 are actually known. This would be a major breakthrough. And one of the results that appeared from this work, consequence, was that there's something called the HP spaces. So these are like the LP spaces. These are kind of you have H2, the Hardy space. HP spaces are something called a Banach space. They're not Hilbert spaces. They're not inner product spaces. So we were able to show that if you prove this approximation problem here for some p between 1 and 2, then you can get not the Riemann hypothesis, but that zeta is zero free for real part greater than 1 over p. So in other words, if you weaken the topology, because when p is less than 2, you get a weaker topology. So then approximation should be in principle easier to prove. Then you can actually prove a weaker version of the Riemann hypothesis. Okay. So this is the final slide, because I think I should finish within an hour, right? So the final slide is one of the main results of this more recent work from last year. And the idea here was to generalize everything we had found, because we realized that if you solve these approximation problems, in fact, one of my students is here. In fact, Francisco, I believe he's listening to the talk. Francisco, you're here, right? I think he's here. Well, he was here. Yeah. He's here. So Francisco is my PhD student, one of my PhD students. So we're working, in fact, with him, continuing this work. He did his master's with me as well. In fact, he started studying since bachelor's with me. So he was a bachelor student when he started reading about these things. So it's not impossible, you know. If you start, you write emails to people, you can learn. You'll be surprised. People will be happy to help you. So this last idea was that rather than looking at Hardy spaces, what happens if we change the spaces? What if we start looking at a variety of spaces? Can we form a theory? Like, what is the relation? Because we noticed that if we weaken the topology, we can still get results about zeta zeros. We don't need to be so ambitious in trying to solve the Riemann hypothesis. Maybe we can extract other information about zeta zeros by changing the spaces. And that was one of the results that we had from last year, that if you have any topological vector space of analytic functions, which does have these very abstract properties, that the polynomials or the monomial zk form a Schauder basis. Schauder basis, just think of a basis. It's a basis in the space, and it contains the Hardy space with a weaker topology, meaning that it's a space which is larger than the Hardy space, but it has a weaker topology. So for example, you have the Hardy space of analytic functions, but it is contained inside the space of all analytic functions, which has a much weaker topology. Okay? And if you can solve the approximation problem there in this space, and the last property, which is kind of more harder to understand, that is, there are these functionals which we define on that space. And if they are bounded linear functionals for all R, so they're defined like this on the monomials, because the monomials form a basis. And if these functionals are bounded linear functionals for all S in some half plane to the right of R, so if such a space exists, and satisfies this checklist, then the zeta function will be zero free in that half plane. So this was a very interesting result. This was really an idea of the undergraduate student I was telling you about, which then we developed rigorously. He's now doing his PhD. So the idea was that we've reduced the question of searching for zeta zeros to the question of searching for vector spaces with certain properties. So this is a new perspective which we're currently, which is, you could say, the state of the art. And of course, all this work is quite recent, 5-6 years. There's many other works that we have, preprints, and we hope that, of course, more people will become interested in this. Until now, my experience has been that people who are interested in functional analysis or Hardy spaces, they're a little bit afraid of going into Riemann hypothesis, because obviously when you try to attack the Riemann hypothesis or study it, people look at you strangely, like, yaar, is bande ko kya masla hai? Ye to theek nahi hai, mujhe theek nahi lag raha. So there is always this suspicious look people have when you go to conferences. Oh, that's the guy, you know, he's losing his mind, he's working on the Riemann hypothesis. But no, I encourage you guys to never think in this way, and you know, just continue focusing. And remember, you know, we have this thing in Pakistan. I'll say it in Urdu so my student can't understand. You know, in Pakistan, a lot of times, मेरे ख्याल में पाकिस्तान में होता है इस तरह के हमारे parents भी ना were like, work hard and just sweat and etc. And sometimes हमसे कभी कभार भूल जाता है, to enjoy yourself as well. And mathematics is fundamentally something enjoyable. I know ये मुश्किल लगता है, and it is true, you need to work hard to be able to enjoy it. Lekin I promise you कि मतलब the harder you work, you will enjoy it, and try to focus on the fun aspect because it is fun. It's hard for you to see now, but it is actually fun, and you learn the best when you're having fun. Okay. So of course at this point it's hard for you to see that, but try to see the fun in it and don't be shy to ask questions. So I think I'll end there. Thank you very much um, for the attention.
Thank you, Waleed. You presented, very non-trivial concepts of mathematics in a very, intuitive way. So I think all of us enjoyed the talk. So thank
Thank
you.
you.
I think there might be some questions. Jeevajo, any
Absolutely.
questions?
Thank you so much, sir. First of all, I have a question that, sir, Riemann hypothesis is considered with one of the most difficult unsolved problems in mathematics. What motivated you to work in this area?
So that's a good question, Samina. Samina, right? Samina Noor, are you my relative? Are you related to me? Because I'm Noor
Yes.
as well. And I'm just joking because of course we have many Noors, right? We have the famous film director also. Uh, so that's a very good question. So actually, I never thought of the Riemann hypothesis or the number theory or these open problems, but I do remember. In fact, I'll tell you a story. So when I was studying calculus with Professor Ghori, QK Ghori, Professor Ghori was our teacher. And I remember I had already started studying a little bit of linear algebra on myself, and I was very curious, and I found a Hilbert space there. And I saw the definition of an inner product on some Hilbert space in L2 as an integral. And I remember I wrote a small paper, not a paper, like I wrote something and I sent it to Professor Ghori, and I said, is this what's going on? Are they treating function spaces as if they are like infinite dimensional spaces? I didn't know about functional analysis at that time actually, but I was kind of trying to guess these things, and I remember the comment of Professor Ghori. He said, "Ah, beta, this is TK. It's something like this, but it's something like this. Like, and it'll take you a while to understand." So I remember his comment. He said, "You're almost on the right track. Like, rigorous itna nahi hai." So I was always interested in spaces and infinite dimensional spaces, but the interest in number theory actually came after I got a job here. So it's really just in the last 5 to 10 years. And like I said, I started studying from the beginning, um, from scratch completely, number theory. So I started from the completely beginning. I picked up a book at the undergraduate level and I started studying from the start. And that's how I became. I mean, I knew about the Riemann hypothesis, obviously. It's a famous open, and I just wanted to understand it. But that's how I actually got interested in it. And I was just lucky that I found some connections and very good students who helped me.
Yes, sir. Thank
And
you.
you have,
Or I have also a second question that,
sure.
sometimes most students find abstract subjects very challenging. What advice would you give us to motivate it and build strong foundation for advanced research?
So abstract subjects. So look, the thing is that in mathematics, there's pure mathematics, there's applied mathematics, there's many areas of math. Even within mathematics, there's many different areas which are less abstract, that are more concrete. So my advice for you to be not to be afraid of abstraction, but to find the particular things that you enjoy the most. I know this is hard right now, but now with the internet, you have access. I was telling your colleagues, your friends earlier that when I was a student, so internet was quite new. We had dial-up, but I found MIT's website at that time, and I was very lucky. They were putting all their coursework online, so I could follow what they were doing, and I could see the outlines, I could see the books, you know. And so my advice, even here in Brazil, is always to ask students to first find out what you enjoy. what you feel. Look, I can imagine maybe you like algebra more, maybe you enjoyed groups theory more, maybe you enjoyed discrete math more. There's so many different areas of mathematics with very different flavor. Maybe you like analysis. From my experience, not many people liked analysis in Pakistan. Um, but we have a lot of good algebraists, of course. And then there's applied mathematics also. Of course, in Pakistan, applied mathematics means we have a lot of people in fluid mechanics, of course, that work. But there's so many other areas. So my advice would be to focus on what you like. Try to use the internet. You can find very simple, very beautiful books. They're easily available now. Springer and other, they put them out for free. And then you can even contact people there and read about it. Do some self-study as well. Because obviously you can't expect your professors to teach you everything. But try to find something you enjoy. I think enjoyment is very important. Other than that, once you enjoy it, I think abstraction will be easy for you once you enjoy the thing. Okay? That's my
Yeah,
advice.
sir. That's true, sir. I will do practice it. I invite students to ask their question if anyone have.
Yes, I have a question.
Yes, Adam.
Thank you so much, sir, for your wonderful presentation.
You're
I have this question. I think I took a course last semester on the advanced inverse problem, then inverse and wave, something I have forgotten the exact title of the course. Then we studied Riemann derivative, Riemann integral, Caputo derivative, and integral. So are they in any way related, like the Riemann derivative with the Riemann hypothesis? Are they really in any way related?
Yeah, they are related. It's the same Riemann. Other than that, so sorry, Adam. So you said Adam, right? Or Adam.
Yes,
I
yes,
think you're a foreign student, right? You're a foreigner working in
yes,
COMSATS, studying in
yes.
COMSATS. Yeah,
Studying, yes.
you're studying. Sorry, you're studying in COMSATS. No, that's
Yes,
great. Yeah, welcome to Pakistan.
yes, thank
So
you.
you're welcome. So you said you were at IMPA. You were in Brazil?
No, no.
Oh,
Have
sorry, I
you?
misunderstood. Because IMPA is the name of one of the main institutes of mathematics in Brazil. I thought you said, okay, I misunderstood.
Oh, I'm
You,
He
currently
was
in
sorry,
Pakistan.
he was saying the course name, inverse
The
problems.
course name is inverse problem.
oh, sorry, inverse problems. Okay, inverse
Yes,
problems. Yeah, no, this inverse
yes.
problems, of course, is a very deep area, of course, of applied mathematics. And I, I'm sure, I believe there's no direct relation between the concept of Riemann hypothesis or Riemann zeta and the Riemann-Caputo derivatives. I think they're used in differential equations in other areas, but I don't think they're directly related. No, it's just because Riemann is involved, I think. But he was involved in so many things.
All right, sir. Please, sir, can you go back to the graph? I want to ask a question.
This graph?
Yes,
Okay.
yes. These fractional parts, no, from I'm seeing one by 5x.
Yes. Ah, you want
Uh,
to see you want to see the
yeah,
definition? I removed
yes.
it. Oh, I removed the, where
Okay.
did it go?
So I wanted to ask the x is it that the x is constant? We are not changing the x
No, x is not constant. The lambda is constant.
because I observed that as you are changing, you use 1 by 5. You also use 1 by 100, but the x still remains. You didn't really touch the x.
Yeah, because it's a function of x.
Okay,
So
so I
I
was
was changing.
expecting since we are plotting a graph, so definitely we are going to use a particular value of x. So I was expecting that.
No, so the particular values of x are plotted here between 0 and 1. So when x is equal to 1, its value is 1 over 5. When x is equal to half, its value is 2 over 5. So it's a function of x. This is the graph of this function when lambda is 1 over 5. That's why I was changing the values of lambda, because for each lambda you have a different function. This is a family of functions. Okay?
Okay, okay.
Yeah. So this is the graph. I don't know why it disappeared. I don't know how to use it. Ah, here it is. Yeah. Okay, here it
Yes,
is.
yes. So you can see 1/5 x, then x is still showing. So I was
Yeah.
thinking,
Yeah, x is the variable. Exactly. It's independent
yes.
variable. So this is plotting for me the graph for x between 0 and 1. Yeah.
Yeah, okay. This is really, this course is really complicated, but with time, we hope to, just as you said, we really need to engage in self-reading. Then, because we can't really expect the professors to show us everything, it's not possible. So they only show us the way, then we have to follow the way.
Absolutely. And it's also not fun, Adam, you know. If someone shows you something, it's also not fun. The fun is in the discovery, actually, you know. And of course, you will follow the path of people that have already tread, and it's exciting following those footsteps. But if someone just shows you, it's actually not fun, you know. It's like, I don't know how many of you guys play video games. I love video games, you know. I've played video games since I was a child. It's like watching someone else playing some video game and you engaging, you know. So I know probably your professors are saying, how, why did he say that? You know, you shouldn't be playing video games in Pakistan. You know, parents say, don't waste time, beta, you know. But no, I'm not encouraging you to play video games. I'm just saying that, you know, I also play video games as a hobby to pass time sometimes.
I think playing video games is kind of acceptable now. Making
I
contents on
really,
TikTok is not acceptable.
because of Arsalan Ash, you know, because the Pakistanis are very good in a particular video game tech, and so they're world champions actually. Yeah. No, I think some video games actually sharpen your reflexes. In fact, they're used in therapy in a lot of places for treatment in America for autism and other things. I think they can be um, very good for reflexes and khair.
It's a yes,
Yeah,
it's good for some
yeah.
mental diseases.
Yeah, मतलब अब मैंने तो यही कहना है ना, I'm going to justify it because I've been playing it बचपन से.
I know, no, I know few people. They were advised to play video games.
Really, yeah, yeah, yeah. Yeah, I've been told. So, Adam, was there anything else? That's a very
Yes,
good
yes.
question.
I have one thing to ask. It's not really a question, but it's like a form of, if possible, I want you to advise us. I observe something with student most of the times. You know, sometimes students don't really want to understand. They prefer to memorize. You understand what I mean? So in such
What?
a case, does some students really like memorizing? Just to memorize during exam, just write what they have memorized. So, and you know, if possible, mathematics is not really meant to be memorized. We need to really understand, if possible. Memorizing just to pass exam is not really the solution. So, please, I want you to
Absolutely.
really speak in this regard.
Absolutely. Thank you for that question. This is memorization is the curse of our education system. I mean, I'm look, I'm here. I'm a product of the Pakistani education. I mean, all my education was in Pakistan. You have to realize, not just my bachelor's, my PhD was in Pakistan as well. So I know the Pakistani education system very well. I mean, I'm completely a product of Pakistani. So, and it's one of the reasons why so I know how serious the memorization issue is. I mean, people, it's one of the main banes of our existence in Pakistan. Not just education, but even other things. We just want to memorize everything and not understand it, right? I mean, I usually tell people that my students in Brazil always ask me that what languages do you speak? And I'm like, okay, I speak Pashto, I speak Urdu, now I speak Portuguese, I speak English, and then I'm like, and then I say I speak half Arabic, and they're like, why half Arabic? He said because we were taught to memorize and not understand it, which is such a shame, which is such a shame, and because it's a missed opportunity. If you think about it, we're not taught to actually understand Arabic. We're asked to memorize Arabic, you know. Uh, so I mean, it's much deeper. This problem of memorization is quite. I'm not saying there's anything wrong with it, but it's a shame that we aren't encouraged to learn Arabic. You know, it's a beautiful language. You know. Of course, it helps us read the Quran and then we could understand it ourselves also, right? Rather than just memorizing it. But yes, memorization, rote learning is a problem in our education system. And I know it's hard. I know it's very tempting for you guys in exams to just memorize what, the theta in the class, the wrote in his notes. But let me just tell you that it's maybe tempting, but it's not good at all. For you, I think it's much better to struggle it out, to try really hard to understand, ask people, message people, ask students. Even if you can understand a little bit of it, it will stay with you for the rest of your life. And the problem with memorizing something is that you will forget it. You will forget it the next day. You will not have understood it, right? And once you understand it, it's like it's a memorizing. I think the analogy is a bit like if you go to the gym or if you work out building some muscle, for example. It's a bit like watching a video of people building a muscle rather than actually doing it yourself. Because when you understand something, you're developing your muscle in your brain. You're developing your capacity. You're forming new neural connections in your brain when you understand concepts. That is why it is worth the effort. Okay? Because when you understand a concept, you are changing. Whereas when you're memorizing, you're just repeating like a parrot, like a tota, right? Tota is parrot in. So I hope that answers your question. You shouldn't memorize things. Stop doing it. Yeah.
Thank you. Thank you. Thank you so much. Thank you so much.
You're welcome, madam. Any other questions? Because if you memorize, you're just.
I have a question.
Sorry, sure. I just wanted to add, Saad. I just wanted
Thank you,
to add
sir,
that
for your nice
memorizing.
presentation.
Yeah, Saad, I just wanted to add a last comment before you start. I just wanted to say, because see, whenever
Okay.
you memorize something, for all of you guys, just